In Chapter 17, we covered expected utility theory, a neoclassical theory about how individuals make choices in the presence of risk. An alternative theory, known as prospect theory, has emerged from psychology and has now made it into economics through the field of behavioral economics. We'll motivate this theory here by appealing to a famous experiment in psychology. In this experiment, two different groups were given different choices. In Group 1, individuals entered a room, were given $1,000, and were then asked to choose between two different options. Under option 1A, they would simply get $500 more. Under option 1B, they enter a lottery where we flip a coin, and if the coin comes up heads, they get an additional $1,000, but if it comes up tails, they get nothing in addition to the $1,000 they got for entering the room. Individuals in Group 2, on the other hand, are given $2,000 when they enter the room. They are then given an option 2A, under which they simply have to give up $500. Under option 2B, they enter a lottery where we again flip a coin. If the coin comes up heads, they have to give up $1,000, and if it comes up tails, they don't have to give up anything and get to leave with their $2,000. In each group, individuals are therefore offered a safe option and a risky option. But in Group 1, it turns out that about 85% of all individuals choose the safe option, whereas only about 30% of individuals in Group 2 choose the safe option. We'll begin with expected utility theory, as outlined in Chapter 17, under the assumption that individuals are risk-averse. Recall that under that theory, we can represent the tastes individuals have over risky gambles through an expected utility function, assuming an underlying utility-consumption relationship that's concave when individuals are risk-averse. We'll assume that individuals walk into the experiment with a current consumption level of X. That implies that if the experiment really goes well, they'll walk out of the experiment with a consumption level of X plus 2,000. Individuals in Group 1 came into the room getting an initial $1,000 and are then offered one choice, the risky choice, under which they enter a lottery where we flip a coin, and if the coin comes up heads, they get another $1,000 for a total of $2,000. Individuals in Group 2, on the other hand, are given $2,000 as they walk into the room, and are given the option of entering a lottery where if the coin comes up heads, they lose nothing and get to leave with $2,000. The worst-case scenario for individuals in both groups is that they'll leave the experiment with their initial consumption level X plus $1,000. Individuals in Group 1 enter the room and get $1,000, and if they choose the risky option and the coin comes up tails, they'll get nothing in addition. Individuals in Group 2, on the other hand, are given $2,000 as they enter the room, and if they enter the risky gamble and the coin comes up tails, they have to give up $1,000 and thus get to leave with only $1,000. If individuals in either of our two groups choose not to take the risky option, but rather go for the sure bet, they will leave with $1,500. Individuals in Group 1 enter the room, get $1,000, and option 1A is that they get an additional $500 without entering any risky gamble. Individuals in Group 2, on the other hand, get $2,000 as they enter the room, and the safe option is that they are asked to give up $500, leaving them with only $1,500. Under expected utility theory, the safe option for Group 1, option 1A, is therefore exactly the same as the safe option for Group 2, option 2A, giving the same utility level for both. Entering the risky gamble is also the same under expected utility theory for individuals in Group 1 as it is for individuals in Group 2. In both cases, the good outcome is that the individual leaves with $2,000, and the bad outcome is that the individual leaves with $1,000. Both outcomes occur with probability 0.5, implying that we can read the expected utility of the gamble from the line that connects the two options halfway along that line. Since the options are the same for individuals in Group 1 as they are for individuals in Group 2, the utility of the risky option should be the same for both groups under expected utility theory. And since the expected utility of the risky B option is lower for both groups than the utility of the sure bet, we would expect risk-averse individuals in both groups to choose the safe bet A over the risky gamble B. A risk-averse person, on the other hand, would choose the risky option over the sure bet in both groups, according to expected utility theory. Both choices are therefore possible under expected utility theory, but if we randomly select people into Group 1 and Group 2, we would expect to have about as many risk-averse individuals in Group 1 as in Group 2, and so we would expect about the same number to choose the safe bet versus the risky option. The fact that many more people choose the safe bet in Group 1 and the risky bet in Group 2 then tells us that something else might be going on.